pumping liquids. Now the situation we have is we have a container of liquid fluid, say something like this. And it's filled with a liquid. And you would like to know how much of energy or work you will need to do to drain the liquid from the top. So suck the water out and take your siphon all the way down to the bottom. How much work to lift that water out. Now, it's quite a complicated problem. Because, you see, you can take yourself a bucket or a pail and you can start scooping the water out. And you know you will be quite excited when you start. But when you come down here, then you have to pump it out with your pail. You know you are doing a lot of work now. So the work to drain this water is quite complicated because you've got different depths. And basically what you have to do is lift water or something like that, which has a mass. Now this will say it has molecules in it. And because it has mass on Earth, it has weight. That's to say, the amount of force you will need to hold it up. So we need to understand a little bit about weight, which is a force. Weight is a force. Water, which has molecules in it, let's just say mass. Force. Molecules. So, if you are looking at a fluid, the first thing you need to understand is the density of that fluid. The density of the fluid. That is to say, how heavy per unit of volume is that fluid? Now, you may say to yourself, well, if you think about water, is water very dense? Water is extremely dense. Ask the people in Japan when the tsunami came. That water is extremely heavy, very, very heavy. You can take a look at some of the videos, you'll be astonished the force that water carries. Water is very, very heavy. Anybody know the density of water? Huh? No. So, water is very dense.
That's 19.9.
Huh?
So 1.9.
9.8.
Please do not confuse density with gravity. We're talking about this and a container of water of that dimension. Which one's heavier?
Water.
That is density. Or the same thing, a piece of gold of that size, a body razor of that size, and a container of water of that size. Try to lift it up. Which one is heavier? That is density. It's got nothing to do with gravity. The density of water, so this is about a meter by a meter. Does it look like a meter to you? No? How about that?
Sure. Close.
Now you take a meter by 1 meter by 1 meter of water. What is the mass of that? Water. 1,000 1,000 kilograms. So that will tell you that water is quite heavy. Nobody will be able to pick that thing up. It's quite small actually. 1 meter by 1 meter by 1 meter water is 1,000 kilograms. That is to say, 1 metric ton. Very heavy. We call that the density of water. So the density of water is what? That is the mass. The density of water. Yes.
It's massive volume, right?
Yes. What's the density of water? I just told you.
Approximately is 1,000.
No, exactly.
That's approximately is 1,000, right?
So the density of water is what?
1,000 That's 999.
1,000?
Per meter.
1,000?
1,000 kilograms per meter cubed.
Yes. 1,000 kilograms in every cubic meter. 1,000 kilograms for every cubic meter. What I said. So in other words, if you have 5 cubic meters, you have 5,000 kilograms of water in there. It's all common sense. It's all common sense. Now, the question becomes, what is the weight of that water? So let's say you have 8 cubic meters of water. What is the weight
Depends on the planet you're on.
on Earth? You will take the mass and multiply it by a gravitational constant, which on Earth is about
9.8.
9.81 meters per second squared. This is acceleration, mass times acceleration. Now there is pretty much all you need to understand about water. Now what you are going to have, you are going to be given a volume and be asked to find the weight of that water. That is to say, how much of force will you need to apply to lift it up. So if you're given the volume, the first thing you will need to do is find the mass. So if you're told the volume is 8 cubic meters, you say 8,000 kilograms. If you say the volume is a half a cubic meter, you say 500 kilograms. Who's to say what the volume is like? Huh? You have quite strange volume. And we need to determine the volume, multiply that by the density to get the mass. And then once you have the mass, you will multiply that by 9.81 to decide how much of spinach you need to eat to hold it up on Earth. That is the weight. So now we can talk about these pumping liquid problems. Now these pumping liquid problems is really a good conceptual probing of your understanding of the integral calculus. Because I cannot give you any formulas. I can tell you what is the concept. is the conceptual thing you will need to do to find the work needed to lift all of this water or pump it out from this tub. Because who's to say what the geometry is? You could have something like that. Or you could have something like that. Pump it out. Or you could have something like this. Pump it out. So the geometry is really, I cannot give you a formula for every possible geometric configuration you're going to get. How much work to lift all of this water out? How much work to lift all of this water out? How much work to lift all of this water out? How much work to lift all of this water out? But the principle is the same. The principle is really the same. Now, the problem with these things is that you're lifting this water out, and then you're lifting this water out, and then you lift this water is takes much more work to lift than that one. Or this one takes more than that one, but less than this one. That is to say, if you were to break it up into a little bucket of water, say this bucket of water, lift it, this one's a little harder. And this one's a little harder. Oh, this one's quite hard. So it seems to me that we need to break this problem